We're always on the hunt for the next revolutionary material. But what if the next big thing wasn't just about making materials stronger, but making them, well, smarter? Today, we're diving into some incredible materials that aren't just tough, they can literally tell you when they've been damaged. Just think about that for a second. What if the armor on a vehicle, or maybe the wing of a jet, could actually feel an impact? Kind of like how our own skin feels a pinch? And then what if it could send out an alert that says, hey, I'm hurt, right here? This isn't science fiction, folks. This is the absolute cutting edge of material science, and it's happening right now. And that leads us right into our first big idea, this constant, ongoing quest for super materials. Especially for industries like aerospace and defense, finding things that are lighter, stronger, and safer isn't just a nice to have, it's the mission. So here's the puzzle engineers have been trying to crack for ages. How do you get the raw strength of metal, but with the feather lightweight of plastic? Well, the answer is in composites. These amazing materials where you combine super strong fibers with a polymer matrix to literally get the best of both worlds. Now, the researchers in this study, they zeroed in on two main ways to build these hybrid composites, using a mix of glass and carbon fibers. They're called interply and intraply. Yeah, the names sound pretty similar, but the way they're put together is totally different. And that difference, as you'll see, is everything. Okay, the easiest way to wrap your head around this is to think about cake. Seriously, on the left, you've got interply, which is basically a layer cake. You have a clean sheet of carbon fiber, then a clean sheet of glass fiber stacked right on top of each other. But intraply, on the right, is more like a marble cake. The carbon and glass fibers are woven together into one single fabric. It's all mixed in right from the start. So, you've baked your two different kinds of high-tech cake. What's next? Well, you've got to see what it takes to break them. It's time to put these new materials through the ultimate stress test. And check out the setup they used for these tests. I want to be super clear. This isn't some computer simulation. Nope. They used a custom-built gas gun to literally fire projectiles at these panels at incredibly high speeds. This is all about seeing what happens in a real-world impact. Think shrapnel or flying debris. And they didn't just use one type of projectile. They tested two different shapes to see how that would change the outcome. On the left, you've got your basic cone shape, really designed to pierce. But on the right, that's a stepped cone. See that sharp 90-degree angle on its shoulder? That little detail is about to become very important. Okay, so before we look at the results, what do you think? Take a guess. Which one of these is going to be harder for the composites to stop? The simple, smooth cone or that more complicated stepped cone? Let's find out. All right, it's time for the big reveal. Let's look at the breaking points and, more importantly, the breakthroughs that came out of these tests. And here is our first major finding. This chart shows what's called the ballistic limit. That's just a fancy way of saying the exact speed a projectile needs to barely punch through the target. And as you can plainly see, the stepped cone, those green bars, required a much higher speed to get through than the simple cone in blue. The shape of the threat matters a lot. Just how much does it matter? The stepped cone needed up to, get this, 42% more energy to break through. That is a huge jump in impact resistance, all because of the projectile's geometry. And here's what all that energy absorption actually looks like. These are the backsides of the panels after they got hit. You can see those distinct damage patterns where the fibers just got shredded and stretched. The big takeaway here was that the layered interply composites, our layer cake from before, generally did a better job and soaked up more energy before they finally gave out. But just being strong and stopping things is only half the story. Now we get to the most futuristic part of this whole thing, making materials that can actually feel the damage as it's happening. The magic behind this is a property called piezoresistance. Now it sounds complicated, but the idea is actually pretty simple. A material's ability to conduct electricity changes when you put it under stress, when you stretch it or squeeze it or break it. And because the carbon fibers in the composite are conductive, they act like a built-in nervous system. So how'd they measure this? Well, they ran a constant, tiny electrical current through the material. When a projectile slams into it and starts breaking those conductive carbon fibers, it's just like snipping a wire. The path for the electricity gets disrupted and the resistance shoots way up. They could measure that spike in real time at the exact moment of impact. Now, one of the most surprising things they discovered was about sensitivity. You'd probably think that having more conductive carbon layers would make it better at sensing damage, right? But it was actually the opposite. With too many electrical pathways, breaking a few of them didn't really make a big difference. But the materials with fewer carbon layers had a much more delicate electrical network, so any little break caused a massive, easy-to-detect signal. So, we've got materials that are tough and they can feel damage. But the researchers wanted to push things even further. They decided it was time to add one more thing to the recipe, a sort of secret ingredient. And that ingredient was liquid metal. Yep, you heard me right. They mixed tiny amounts of a gallium-indium alloy into the epoxy that holds the whole composite together. And just look at the results. This chart clearly shows that adding just 1 or 2% of liquid metal made the materials even harder to penetrate across the board. And this wasn't just a tiny improvement. Adding just 2% liquid metal boosted the stopping power by up to 20%. The theory is that those dense little droplets of liquid metal help absorb and spread the force of the impact way more effectively throughout the material. So let's bring this all home. Let's wrap this up and really think about what these discoveries mean for the future of, well, not just smart armor, but all kinds of next-generation structures. So if you're going to remember 4 things from this, here they are. First, the shape of the threat is a huge deal. Second, how you build it matters. Our layered cake composite was tougher than the mixed batter one. Third, adding a little liquid metal gives you a serious performance boost. And finally, the coolest part, these materials can be engineered to feel and report their own damage live as it happens. And that leaves us with one final, really big question. From airplane bodies that can signal they need repairs after a rough landing, to a soldier's helmet that can report its own structural integrity after an impact, what else could we build with materials that know for themselves when they're broken? The possibilities are really just beginning to open up.